over some of the challenge problems. And, you know, I want to make it clear that these are definitely tricky problems, and you're not expected to, you know, be able to do all of these without help. They're meant to be done in groups with guidance from me, so, you know, don't be freaked out if these were really hard for you. But let's go over a few of them. In this first problem, I ask you to consider the following 8 points, and suppose that you want to draw line segments, okay, between these points. Here's the question: how many line segments could you draw between the points? There's a couple ways of doing it. One way would be to say, oh, well, let's start by considering all of the segments which come from this point right here. I guess that would be 1, 2, 3, 4, 5, 6, 7. So 7 segments from that point. And then you could say, well, let's consider all the segments going from this point. Now, there wouldn't be 7 because you've already counted this segment here, right? So by considering segments coming from this point, you actually only get 6 more. So that would be 1, 2, 3, 4, 5, 6. And then when you get here, this segment has already been drawn, and this segment has already been drawn, which means that you're only going to get 5 more. So 1, 2, 3, 4, 5. So the total will be 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, which I think is 28. Now there's an easier way of doing it. There's a very clever way of doing it. It's to recognize that choosing an edge really just means choosing a pair of points, an unordered pair of points. If I call this point A and this point B, then these 2 points determine an edge, determine a line segment, this one right here. But it's important to note that segment AB is the same as segment BA, and for that reason, to count the number of possible edges, all I really have to do is count the number of pairs of points, right? Specifying a pair of points, like this point and this point, specifies an edge. So the number of possible edges is in fact exactly the number of pairs of points, where order doesn't matter, right? Because AB is the same thing as BA. So how many pairs of points are there? Well, you have 8 points total, and if you want to consider the number of pairs of points where order doesn't matter, that's going to be simply 8 choose 2, right? That's the number of ways of choosing 2 objects out of 8 objects where order doesn't matter. And that should also be 28. Okay. In general, how many line segments can be drawn between endpoints of a similar configuration? So instead of 8 points, suppose you had n points. Well, it's very easy to generalize this formula right here, right? Instead of, if there were not 8 points but n points, there would just be n choose 2 segments, okay? Finally, suppose you have n points and you draw all possible line segments between the points. When you finished, you have 55 line segments. What is n? Well, we know that the number of line segments that are possible is n choose 2. And so if that happens to be 55, then we have the equation n choose 2 equals 55. Now you have to solve that equation for n. The way you should do it is recognize that n choose 2, there's a formula for that. It's n factorial over 2 factorial times n minus 2 factorial. Now, you may wonder how in the world are you supposed to solve this equation with all the factorials floating around. The thing to understand is that most of the terms in this fraction are going to get canceled, okay? N factorial means n times n minus 1 times n minus 2 and so on. N minus 2 factorial down here means n minus 2 times n minus 3. Many of the factors from here are going to cancel the factors up there, okay? So if you actually write it out, let's actually write it out. So what is n factorial? That means n times n minus 1 times n minus 2 times n minus 3, all the way down to, I suppose it's going to end with like 3 and then 2 and then 1, right? All over 2 factorial just means 2 times 1, in other words, just 2. But n minus 2 factorial, that means n minus 2 times the next one down, which is n minus 3, and so on until you reach the bottom, 3, 2, 1. And that's supposed to be equal to 55. Now the point here is that most of these terms cancel. The n minus 2 cancels this n minus 2. The n minus 3 cancels this n minus 3. This 3 and so on, right? So the only thing that's left over in the numerator, after all that cancellation, is the n and the n minus 1. So that's n times n minus 1 over 2 is equal to 55. You can then solve that equation. It's a quadratic equation. I forget the answer off the top of my head, but from here out, it's pretty easy. Let's think about number 2. So, you've got this grid problem, and the question is how many paths can be drawn from this point to this point right here, from x to y, such that you only move to the right and down. So, like, for example, this could be a path, right? Or maybe all the way to the right and then all the way down. How many such paths are there? The hint that I give you is that every path can be represented as a word involving d's and r's, d meaning down and r meaning right. For example, if I take this path here, just going all the way down and then all the way right, that means I go down 1, 2, 3, 4, 5, 6, 7. So that's like 7 d's. 1, 2, 3, 4, 5, 6, 7. Followed by 1, 2, 3, 4, 5, 6, 7, 8, 9 rights. So that's 9 r's. 1, 2, 3, okay. Now, so this particular path going all the way down and then all the way right is encoded in this word, all d's followed by all r's. The key insight here is that no matter what path you take, whether it's this one or some combination down and right, whatever you do, there are always going to be 7 d's and 9 r's. Doesn't matter what path you take, you always have to go down 7 times in total and right 7 times in total to reach this point, which means that every path, okay, is really just some rearrangement of these 7 d's and these 9 r's. Like this squiggly path would be down, so d, r, 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 d, 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 r, 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 d, and so on, right? So the number of paths is actually exactly the same as the number of rearrangements of this word, okay? Now, how many rearrangements of this word are there? Well, because there are repeated letters, the typical algorithm of saying, what is the first letter, what's the second letter, doesn't work. Instead, you should imagine that there are a total of 16 blank spaces, right? There's a total of 16 letters. 16 blank spaces, and the first step for creating a rearrangement of this guy would be to just place, say, all of the d's at once. So step 1, choose which of the 16 spaces are going to have d's. So how many ways can you do that? Well, 16, choose 7, right? Once you've done that, you're actually done, because once you place the d's, right, in the 7 spots, wherever they are, you know that the remaining blank spaces have to be r's automatically. So there's actually nothing else to do. So 16, choose 7 is the correct answer for the number of paths. Okay. Let's move on to some other questions. So if you read this description, so I tell you a graph is really just, a collection of points. And if you're watching this, I think it makes sense to try and look at this worksheet on your own before you watch the video. But yeah, so if you read the description, I tell you that a graph is just a collection of points with line segments between them. The line segments are called edges, and the points are called vertices. A graph is called complete if every vertex is connected to every other vertex. In other words, all possible edges are drawn. So for example, this is not complete because you could draw this edge, right? That edge is missing. Neither is this one. So in part 4, I say draw a complete graph with 4 edges, or with 4 vertices. Okay, so here are 4 vertices. We just need to draw all possible edges. So that would be like this, 1, 2, 3, 4, and then these guys right here, and that's all the edges. Now the question in 5 is how many edges are there in a complete graph with n vertices? Okay, so if instead of 4 vertices you had n vertices, how many edges would there be? We actually already solved this problem. It was the very first problem. Well, I mean, actually it's 1b, right? We already answered this question. If you have a bunch of points, how many possible line segments can be drawn? The answer is n choose 2, where n is the number of points. Well, that's the same question here, right? I mean, if you're drawing all the edges, that means you're just drawing all possible edges. So that, there are n choose 2 edges once again. Okay, bipartite graphs. A bipartite graph, you're not going to have to know the graph theory for the test or anything. Graphs are just a good source of examples for practicing counting. Okay, but a graph is called bipartite, right? If there are 2 collections of vertices, where the edges go between the two groups but not among them. So if you notice, all the edges are going between the groups but not within the groups. So this graph here is bipartite. And a graph is called complete bipartite if, number one, it's bipartite and every possible edge is drawn. Every possible edge while preserving it being bipartite. So this thing is bipartite, but it's not complete bipartite because I could draw this edge right here, and that edge is missing, right? All right. So 6 says draw K2, 3. That just means draw the complete bipartite graph with 2 vertices in the first group and 3 vertices in the second. So if I want to make a complete bipartite graph, that means I have to connect, every possible edge except, I'm only allowed to draw edges between the two groups. So I need this edge, this edge, this edge, and I need this one, and that one. And that's the complete bipartite graph with 2 vertices in the first group and 3 in the second. Now, here's a question. How many edges are there in the complete bipartite graph K and M? All right, so in other words, suppose you have n vertices in this group and m vertices in the second group, and you do all the connections you can, you draw the complete bipartite graph. How many edges will there be? Well, let's think of it this way. Start with this vertex here and say, how many edges is that vertex going to have coming out of it? Well, this vertex needs to be connected to every vertex over here, like this one, and this one, and this one, and that one. So how many edges is that? Well, there are m vertices over here. So that's going to give you m edges coming out of this vertex, okay? So you get m edges beginning at that vertex. And by an identical argument, you get another m edges coming out of this vertex, and another m edges coming out of this vertex, and so on. So the total number of edges will be m plus m plus m plus plus plus. How many copies of m do you have total? Well, there are n vertices here. So you have n copies of m. In other words, a total of n times m vertices, edges. Okay? So that's the number of edges in a complete bipartite graph. Okay. Now here's question number 8. How many bipartite graphs exist with n vertices in U and m vertices in V? So similar to number 7, except that, I'm asking you how many bipartite graphs exist if there are n vertices in the first group and m vertices in the second. So I'm not saying a graph has to be complete. There's only one complete bipartite graph of this type. There are lots of other graphs which are bipartite but not complete, like the example which was drawn here. Okay, so I give you a hint about how to do this. I say, for every possible edge, you have to make a choice. Do you want to draw that edge or not, right? And that gives you 2 choices for every possible edge. So, what you do is, you sort of think about every possible edge that you could draw. And for each one, you say, all right, do I want to include that edge or not? And there are 2 choices for each edge. So your algorithm is basically step 1. You look at the first possible edge and you say, okay, do you draw it or not? That's 2 choices. And then you look at the next possible edge and you say, do you want to draw it or not? That's another 2 choices. And so on. So you keep multiplying by 2, right? So you're going to have 2 to some power, and the question is really, what is the exponent here? Well, you have a copy of 2 for every possible edge, okay, which means that, so the question is really, how many possible edges are there? Well, we already found that out, right, in this problem here. We said that the complete bipartite graph has n times m edges, so that's going to be n times m. Okay. Okay, I do want to, I think, I'll talk about number 9 very quickly. So I tell you that, I talk about this power set thing, which is the collection of all subsets. And I ask you, if you have a set containing n elements, how many elements are in the power set? The answer is 2 to the n. Now, why is that? Very similar to the last problem we did. Basically because if you want to construct a subset of the set S, right? Let's say your set is A, B, C. Let's say you want to construct a subset. What you really have to do is for each element in this set, you have to ask, do you want to include that element or not in your subset, right? So step 1, do you want to include A or not? Step 2, do you want to include B or not? Step 3, do you want to include C or not? There's 2 choices for each of those elements, right? So the number of possibilities is 2 times 2 times 2, right? And how many copies of 2 are there? Well, you have a copy of 2 for every element in your set. So if there are n elements in your set, then it's 2 to the n. I think I'll skip 10 and 11. They're a bit less important, but I do want to talk about 12. How many permutations of the word A, B, C, D, E, F, G, H contain the string ABC? And I give you a hint. You should treat ABC as a single block. Then it's like there's only 6 objects to rearrange. Okay, the block ABC and then the other 5 letters. So, basically what you should do is sort of say to yourself, oh, if I want to count, rearrangements where A, B, C are together, then you can basically pretend that A, B, and C are like literally glued together. So those aren't 3 different objects. It's just one object, one block. Okay, the D is still a single block, and the E is still a single block, and the F is still a single block, and the G and the H are still single blocks. So counting the number of rearrangements with A, B, C right in a row like that is just like counting the number of rearrangements of these 6 blocks, right? 1, 2, 3, 4, 5, 6. So how many ways can you arrange 6 objects in order? Well, 6 factorial, because an algorithm is step 1, what block comes first? You've got 6 choices. Step 2, what block comes second? You've got 5 choices, and so on, right? Okay, so I think that's all I'll say about this. I know I didn't go over every problem on here, but I think that that's the most important ones that I wanted to talk about.